Hey guys, Jim Vinosky with Manufacturing Talks. Welcome back. Hey, we're going to geek out today. I've got a guy named Mark Malburg. He has his own company called Digital Metrology Solutions, which sounds really geeky, right? But he's here to talk about something really important to everyone, and that's surface metrology. So when you think about, hey, can we make sure paint sticks? Can we make sure our bearings are completely round? Things are going to work right when you put them together. That's what surface metrology is all about. And Mark is here to tell us all about how that works in the real world and the benefits it brings us. So stay tuned. Mark's going to be with us in just a few seconds here on Manufacturing Talks.
Welcome to Manufacturing Talks with Jim Vinosky. Industry has a million cool stories, and Jim talks to the movers and shakers who are making them happen. Let's dive in.
Hey, everybody. Welcome back to Manufacturing Talks. I'm Jim Vinosky, your host. Really happy to be joined by Mark Malburg today. He is the president at Digital Metrology Solutions, and we're going to geek out today, folks. It's going to be awesome. Welcome, Mark.
Thank you. It's great to be here.
Good to have you here. So this is a topic that came out of nowhere. So I'm just going to throw it out there. I'm a friend of one of the Malburgs that has not been on the show. But as you may recall, I had Dan Malburg on a week ago. Now I've got Mark Malburg on here. We talked nuclear last week, which was nice and geeky. And now we're going to talk surface metrology, which is amazingly geeky. I love it.
Oh, it's the best. I'm gonna just crush what Dan did last week. No family rivalry here at all.
I tried to say it was not a competition, but here we go.
You said that, but that was totally off screen. So this way I own it.
I love it. Well, so before we dive into the engineering wonders of surfaces, why don't you tell us about your background?
Sure thing. I started out as a mechanical engineer, as many people do, and stumbled into this world of metrology through literally a summer internship making measurements, and went back to Michigan Tech and met Professor Jay Raja, who was a premier surface metrologist in the world. Didn't even know it existed at the time.
Wow.
And it started out basically with an introduction saying, "I'm interested in your class." And instead of answering, he said, "Would you like a job?" And that's where it began. I went on and did my master's in surface texture and later a PhD in surface texture. So started out my career as the corporate surface metrologist for Cummins Engine Company through the 90s. And there was enough pull from the outside. Amazingly, people are interested in surfaces that in 1999, I formed Digital Metrology and got to play for a bigger audience.
So when you did that, were there specific things you were hearing out there as far as demand went that made you think, hey, this is something where I can go out and make a living for myself?
Yeah, it was interesting because with Cummins, my job was to solve problems that weren't quite measurable. So we might be able to collect some data, but not necessarily calculate the right things that mattered.
Yep.
And through that, I was interacting with the measuring equipment companies and other suppliers to Cummins. And, my name was getting out through those external things.
Yep.
And people were saying, "Oh, you solved that problem for them. Can you solve this problem for me?" And eventually that pull became great enough. And I formed Digital Metrology. And the good thing is it was a great relationship still with Cummins. They keep me on as a retainer. And it was probably one of the most graceful leaves that I could imagine possible. So I'm really thankful for the team at Cummins. And I'm excited that I've got some really cool stuff that I've been doing the last 25 years now too.
Well, and it's interesting because it's not the geeky part, but what you just said, people should think about that. If you get known for something and people are saying, hey, can you solve this? Can you solve that?
Yeah,
that's an opportunity.
It is. And it was one that I probably spent more time worrying about because you have corporate confidentialities when you're with a company, and you just have to cut those conversations off until some point when you're ready to go full bore. You don't want to be working something in the background and break, relationships and confidentiality. So after that accumulated enough, then it's finally, okay, now let's flip flip the page and go for
Yep.
it.
Yep.
And it's a little bit scary because you didn't build that base before you flip
Hmm.
the page, right?
Yep.
In order to do it well in terms of confidentiality and relationships, I didn't want to be playing for both teams.
Right. Yeah, which is also great advice. You want to approach it um, from that more collaborative mode and keep your options open in the early days for
Yeah,
sure.
I think something that I look back on that I would advise others in that position is try to figure out a way to keep your current employer as your first customer.
Yeah, great. That is awesome advice. And so, we've already thrown around some terms that some folks out there may not recognize.
Yeah.
And I loved stuff you sent me to kind of reflect on before we got on here. And you had the description for surface metrology as questions you get asked like, will this seal leak? Will this bearing chatter? Will this paint stick? So that kind of gives that visual representation for folks who may not be as geeky as you and I around what metrology is all about. So let's dig into that a little more. What are the things that matter to people that allow you to make a living with this?
So I work specifically in the area of surface metrology.
Yep.
Metrology is a much bigger field. Metrology is literally the science of measurement. So there's fluids metrology and chemical metrology and electrical metrology, and everything that has a measurement really has a metrology associated with it. If you narrow that down, there's the world of dimensional metrology, things that can kind of be measured in units of meters or inches. And then within that is my world of shapes. So surface metrology is really anything to do with a shape. It could be roundness, it could be flatness, it could be roughness.
Yep.
And yeah, there are amazing applications anywhere from sporting goods to spaceships. They rely on those surface shapes. They perhaps can't be wavy because it will distort your lenses if there are waves in them. Or perhaps they need to be rough to carry lubrication. So it's an incredibly vast field.
Yeah, and it touches on our everyday lives
Hmm.
in ways most people aren't even going to fathom.
I see
Right?
what you
Things
did
just
there.
work.
That was a hilarious pun. It touches on our daily lives.
Unintended.
Well played, Jim. Well played. Right, literally anything you touch.
Yeah, that's right.
You are just killing it today. That was
Thank you. Yeah,
what a
it's,
great line.
totally unintended, but I'll take it. The one I love is that paint sticking. We
Yeah.
all, when we do our home projects, get ready to paint and we sand things. And
Mm.
obviously, there's a part of that around making stuff smooth so the surface looks good once you've painted. It's not all mottled or pitted or whatever. But we also sand surfaces that are already smooth to make paint stick, right?
Exactly. Yeah. And here's a bit of irony as we try to get a little more engineering on that surface. How would you describe that roughness of that roughed up surface? There's not an easy number to say I roughed it up enough.
Yep.
At first blush, you might say, well, how tall is the roughness? Highest peak to the deepest valley. Well, what if it's a lump instead of fuzz? It still has the same height. What you want is that fuzzy surface.
Yep.
So describing the shape of that roughed up surface is an interesting challenge. What you're really going for is surface area, not surface height. But almost all of the way we describe roughness is height.
Yep.
Height doesn't necessarily matter.
Yeah, it's interesting. And again, in the real world, you see the instructions for getting ready to paint. You'll start with the rough sandpaper and go to
Exactly.
finer and finer. And that final fineness of the sandpaper is to get that particular roughness that you need for the paint.
Exactly. And really in the paint world, we're really talking more about the appearance of the surface,
Mhm.
getting that glossy, smooth looking surface.
Yep.
That's often in industry, from a machine shop perspective, where somebody says, I've got to make that good surface, or I'm going to make that surface better
Mhm.
and better. Most of our engineering applications today, that better surface is actually worse. Because as two surfaces become super polished, And if they're really flat and really smooth, they will actually stick together and they won't
Ah.
slide. So the friction problem is very different than the appearance problem.
Hmm.
And that's where the
Yeah,
field of
interesting.
surfaces really plays in. It's interesting. The field of surface metrology isn't like the other metrologies. In most of metrology, we're striving for the utmost in accuracy, say, of the length of my pen. In surface metrology, we're working more towards the best description of a shape. And it may not be the ultimate length of my pen, it's
Right.
what describes how that paint sticks.
You talked about shapes, and that's another one that fascinates me. I'm a lifelong bicyclist, and of
Yeah.
course, nowadays all your bearings are sealed. But I remember back in the old days, we'd tear our bearings down and inspect the races and inspect
Uh-huh.
the ball bearings themselves for visual problems. But what you're talking about is obviously well beyond visual. So let's talk about that roundness and the
Mhm.
smoothness you need in that realm.
Sure. So let's talk about a bearing race. So you've got a circular ring with a bunch of, say, ball bearings inside it. The race itself is responsible for a lot of the noise as the bearings interact with the race.
Yep.
When we control that race to make the best race, um, we're not just concerned with roundness, but we're concerned with the number of bumps in the roundness.
Hmm.
For example, if we're machining it and the machine chatters as it machines, and we put 14 bumps in a race that's going to have 14 bearings, we have a noisy system. And when I'm talking about bumps here, I'm talking about perhaps tenths of a micrometer. So we're talking, a few millionths of an inch
Yeah.
of
Really, really
slight
small.
deviation, tiny stuff.
Yep.
It's really small, beyond what your eye can see. So we need measuring instruments that, can see these shapes, but those shapes correlate directly to noise. And when we start talking about noise, it turns into vibration. When it turns into
Mhm.
vibration, it turns into contact stresses and wear. So it's not just the overall, is it round, but what kind of round is it,
Yep.
is what matters.
And that noise thing alone is kind of illuminating. Most people don't think about that, but yeah, if you have a fan in your house and it's rattling, that's gonna drive you nuts.
Exactly.
In my bicycling world, if you have a bearing that won't seat properly and it's loose and has play in it, you're not gonna be able to, transfer power to your
Exactly.
wheels as efficiently, and you wind up losing the 100-mile race because
Because
it cost you a fraction of
yeah,
a second.
I'm sure
Um,
it's all about the bearings, not necessarily your training
Has
or
nothing to
anything
do with
like.
my legs. No, it's all the equipment. Now when we talk about, like, the roundness and the surface attributes,
Mhm.
what are the technologies that you use then to be able to see those things we can't see with our bare eyes?
Sure thing. So really the most common technology is a contacting electronic probe. We can do really, really well with an electronically amplified probe, like an LVDT. It's the standard probes that you'd see around manufacturing, those pencil probes that have like spring loads on them.
Yep.
That's kind of the basis for most of our measurements in roundness and roughness and that kind of thing. Now, people that are new to the area like to throw around the idea of why not use lasers? Everything should be a $1 million laser, as Austin Powers might want. So the the idea there is we can, but only in certain applications. Lasers are great for length, and they can be built into some probing. But when it comes to things like surface finish, the spot size of a laser is actually quite a bit bigger than the diamond tip, say, that we would use to measure roughness, kind of like a record player needle tip, only ours are a bit finer. So we have to be really careful when we start thinking anything can be measured with a laser. Now,
Mhm.
lasers are a great tool, but they don't have the resolution many of our systems do today. Now, the area
Fascinating.
that's yeah, thanks. The area that's growing rapidly right now is 3D measurements. We see it in, the handheld scanners scanning the body of a car. we're doing 3D and surface texture and have been for quite some time, but it's really growing in popularity to use microscope-based three-dimensional surface measurement. And we can look at a spot, as big as, say, the tip of my pen and put 1,000,000 points on that tip and
Mm.
see the microscopic texture in 3 dimensions, not just in terms of color like your desktop microscope would
Yep.
see. And that area is growing rapidly right now. People are moving to 3-dimensional as opposed to just tracing a stylus. So we're using optics. We use a lot of electronic probing, and some lasers are out there as well.
Hmm. Of course, in broader industry, we're talking about all the advances that are out there from computer technology, AI, all these different things that have allowed us to automate more and
Mhm.
monitor more and get smarter with our manufacturing. Are there big advances in the metrology world when it comes to the tech side of things?
Yeah, it's fascinating you bring that up because you're kind of hitting a sore spot with me, and you hurt my
Okay.
feelings now by bringing that up. So I'm going to shed a small tear right here in the corner of my eye. We're in an interesting generation that way because people are thinking, lights out and how do we automate and industry 4.0. And I just heard a talk a few weeks ago about quality 4.0. And basically, it's
Ah,
not really defined. It's just a buzzword was the talk. And the person said, when we get to quality 5.0, we'll look back and know what quality 4.0 meant.
yep.
So, and you're probably as good at buzzwords as anybody because I love how tuned in you are to industry. But here's an interesting dilemma in surfaces and this idea of lights out and AI. If I told you that the case on the back of my phone wasn't flat, actually, let's look at my little pop socket thingy here. I said that's not flat. And I told you it's 0.5 millimeter out of flat. And that gets reported through the quality system back through the process management software. My flatness is out by 0.5 millimeter. What would you correct? We don't know.
Hmm.
Is there a gouge in it? Is it bent convex? Is it bent concave?
Hmm.
The numbers we generate for surfaces don't lend themselves to closed loop. And this is a real passion point for me, is if we're going to understand and control surfaces, we've got to play with them. You've got to take that data back to your office and spin it around on your screen and smooth it and filter it and see what shape it is. Take the shape out of it and see what the fuzz and the roughness and the scratches and defects are. Surfaces are shapes, they're not numbers. I joke, and the sound level of, say, a concert. You're a metal guy. Pick your favorite metal band. It's probably 110 decibels or more if you're in the front row.
Right.
I can see you bobbing your head. Um, well, a fire truck driving by is also 110 decibels.
Yep.
The numbers don't describe the experience. And that's the same problem with surfaces, whether it's roughness or flatness or roundness. The numbers alone aren't going to help us solve problems. We've got to use the other side of our brain and be artists and explore the pictures. So I am just passionate about getting people equipped in their office to look at those shapes of a good part and the shape of a bad part. The spreadsheet isn't going to give us that answer. It's not in the numbers.
Hmm. So that's really interesting because it actually plays pretty well with my experience in the manufacturing world. And that is, you can get stuff from the numbers, but they don't give you the whole answer. It's similar if you're looking at a process system.
Mhm.
You can have these key performance indicators you measure,
Yeah,
and if they're off, that doesn't tell you the whole story, right?
right,
Similar?
right.
So you got to go
Exactly.
dig into what's happening out on the floor to get the whole picture and the root cause of the problem.
100%. And I think your experiences and mine are in parallel paths that
Yeah.
way.
Yep.
And it feels a little old school, but it's really the only school because the numbers are limiting.
Yeah. Yeah. It is old school, but it's kind of that necessity of data and analytics can only take you to a certain point, right?
Right. Again, it goes back to the decibel problem.
Yep. Yep.
So decibels changed. Well, does that mean the fire truck drove past the concert or what happened?
Yep.
We still need that experience of some other information.
Yeah. The real world.
Yeah.
Interesting. Okay. Gonna throw you a conundrum here. So you've had a good long career doing this now. What would you say the most critical surface metrology challenge is that you've ever encountered in that career?
Wow. That's a little tricky because some of the tricky ones are confidential. I
Yeah,
think our bigger
I guess.
challenges,
Yeah, I guess just say it, the one that you can talk about.
what I can talk about. I could speak pretty generally on that.
Yeah.
Um, I think some of our bigger challenges right now are dealing, say, under the surface. Let's say something is folded over on a surface, like a burr that's folded over, and we can't measure through it. All of
Hmm.
our measurements are top down.
Yep.
And so, how do I know if I've folded metal over or not? And that may flake off and cause debris and cause problems. So, some of the projects I've worked on in that regard have said, well, I can't measure it's folded, but I can find steep edges. And if I find steep edges, that's going to be correlated to folding. So, some of those kinds of challenges, some of the more interesting problems have been in true 3D surfaces where we're using, say, CT scanning, not just driving a stylus over the surface, but using an X ray and looking inside the surface. But those are, the technologically challenging ones, the ones that I love, the challenges that, get me up in the morning and get me going
Mhm.
are the cases where somebody says this part works and this part doesn't. And we get to have a conversation of what do you mean by works?
Mm. Yep.
Well, it needs to last this long and the bad ones have stripes on them. Well, let's take that knowledge and turn it into math that we can apply in a measuring system. Those are great projects where I
Mm.
can work with an engineer that knows the physics
Yep.
and build a measurement system that has the physics built inside it. So, for example, a customer has engines where some of them are leaking and some of them aren't, but they all measured the same.
Mm.
Back to the
Mhm.
decibels problem. They made the same amount of surface noise, if you will.
Yep.
So we build up the physics of what a gasket does pressed into the surface. And instead of measuring height or roughness, we can measure leakage directly on the shop floor
Mhm.
predictively.
Yep.
So those are some fantastic problems. We're doing the same kind of thing with surface appearance. These surfaces look good and these surfaces don't. Well, what is it that makes that surface look good? And it's a distribution of slopes, not heights.
Mhm.
So those are some of the challenges that I just get, excited about is how do I connect someone's experience to a surface?
Mhm. Yep. Interesting. Now we talked about the technology directly involved in what you do, but then we have new technology in manufacturing. So, for example, 3D printing, additive
Mhm.
manufacturing, is that bringing you guys some new challenges?
Challenges indeed. Again,
A loaded question.
that is a very loaded question. So let's think about my pen as a roughness measuring instrument. So it's a diamond stylus in that case, but a ballpoint pen's a nice analogy. One of our challenges with 3D printing is it can make some very steep slopes. And the cone of my stylus or the cone of my pen here in this example may not be able to see all of the steep slopes.
Mhm.
So steep slopes are a huge problem in typical roughness measurement. So we
Uh-huh.
have better technology, some better optical systems, going to 3D X-ray to try to, take on those challenges. So that's the getting the data part, the actual measuring part. Our next challenge is describing what matters. So let's think of a 3D printed surface. Here's my letter opener. Let's say we 3D printed this vertically for some reason.
Mhm.
I don't know why, but let's just pretend we did.
Yep, for
And we've
argument's
got
sake.
layers. If this was being used in an application where it bends, there's a potential for cracking along those layers.
Mhm.
But that cracking isn't necessarily due to a roughness valley, it's due to roughness sharpness. So if I slice it with a razor blade versus sand a valley into it, the razor blade slice is where it breaks.
Mhm. Yep.
The sharpness within the surface is something I've been working on quite a bit lately. So 3D printing, one, it's hard to measure, and two, the applications are interesting. There are a lot of vibrating applications right now.
Yep. Interesting.
Yeah.
Okay, last question.
hmm
As you look forward with your career and your company, what are the coming challenges that you see down the road, say like next 5, 10 years?
Yeah, I think there are two things I would point to. One is, again, getting our data connected more to what matters. I think as our results, not just the average roughness RA value on a surface, but more what is the predicted leakage of a surface or the predicted appearance of a surface. If we can connect our measurements to what matters, we might be able to start closing that loop better of knowing that we've made good things and even doing the same thing of what is it in the surface relates to the knobs on my machine. Often a company will come to me and say, well, I don't have a leak knob on my grinder. I can't make
Yep.
a
Right.
surface that seals because there's not a turn up the ceiling capability on a grinder.
Yep.
But if we can connect our measurement to the machine controls, so by measuring the surface, I know, did I burn the surface? Did my grinding wheel start to degrade and I need to address it? Can we connect data to controls? Can we connect data to function? As we tighten those loops, we can really do well in industry.
Yep.
The companies I work with that do this very well, some of the racing companies, they're looking at the pictures to control the surface, not the numbers.
Mhm.
They've got, big graphs right next to the honing controls. So tightening those loops. The other challenge, and I'll go back to, and I think this is going to be a culture challenge, is we're in such a data-driven world right now that
Yep.
people are so stuck in their left brain, or left half of their brain,
Yep.
they don't step back and look at worn out parts and look at the shape of the surface that went into it and develop the controls on those things. A great
Right.
example of a company that I work with that's producing shafts. Let's just call them generic shafts for anything. It could be a pump, it could be a wind turbine. They make them smooth and they think they're making them straight. But when you tear the system down and look at it, there are stripes of wear on the surface. Those stripes are not roughness. They're too wide to be roughness, but they're too narrow to be straightness. So there is a wave hiding in that surface.
Mhm.
It's like music playing and the baritones are too loud.
Right.
But you don't know the baritones are too loud because you just hear decibels.
Yep.
And optimizing those shapes is something that we can only do when we see the pictures and see the parts. And getting people back to the world where surfaces are an art, not a number, is going to be very, very important. That's where the innovation takes place. That's where people are making better performing sporting goods, better performing bearings and seals and everything else, is because we're exploring the physics and the shapes, not the numbers.
Another excellent analog for broader manufacturing, because obviously we like to automate things. We like to go
Mhm.
into the data and sit behind screens versus being out in the dirty and noisy plant. But you're absolutely right. That stuff only takes you so far. And unfortunately, as we face this workforce challenge, we try to automate more and more and get people away from that old
Yeah,
school of doing things. But you're truly losing a piece of what needs to happen when you do that, aren't you?
We are, and I think we have the tools, though. We just need to build the company cultures to use them. For
Right.
example, 3D scanning of an airplane wing. Well, I feel like the engineering department should all have that 3D data at their desktops and
Yep.
be spinning it around and looking at it, comparing it to the CAD model, comparing it to the aerodynamics, comparing it
Mhm.
to the functional performance,
Mhm.
not immediately going to the result that it was out of shape by a half millimeter.
Right. Yep.
But why? What shape?
Yep. Yeah. And what does
And
that mean?
right, right. So even if the shop floor is in another country, we have the capacity today to have the data on your desktop as
Yeah.
if you're standing there.
Yeah. That's a
And
great point.
companies need to take advantage of that virtual trip to the shop floor that you and I
Right.
would take physically.
Yep. Yep. Yeah. Very well said. Anything we haven't touched on that folks ought to know about this world that you work in?
No, I think the deal is that it really, really matters.
Right.
People might neglect, say, roughness. Well, that's tiny. I'm going to get the size right, and if it fits together, it works. Well, fit is only one part of making things work. Is it durable? Is it sealing? Is it making noise like your bearings? There are so many other functions beyond fit.
Yep.
And almost all of our drawings are produced through the eyes of fit.
Yep.
Mechanical drawings are about tolerance stack ups and will it fit. Fit is a tiny function, and surfaces tend to be neglected, and yet that's where our warranty problems are. That's where things go wrong. That's where your hip joint wears out and too
Ooh,
soon,
yeah.
or that kind of thing. Did I hit a sore spot there, Jim?
Well, fortunately, I have not experienced that, but I've heard some horror stories. So
Sure.
yeah, I hear
So,
you.
yeah, surfaces matter, and even to the
Yep.
extent one of my colleagues, Don Cohen at Michigan Metrology, has a great statement. Whenever we start feeling inadequate and say, does this stuff really matter that we've dedicated our lives to? He says, Mark, air is small. And think about surfaces and sealing air. Yes, air is
Yep.
small,
For
and we
sure.
work in a small space.
Good deal. Well, Mark, this has been absolutely fascinating. Now, I'm a little biased because I'm a mechanical engineer too, but I have to believe everyone got something great out of this. So I appreciate you joining us today.
Hey, thank you so much for the opportunity. It's fun talking to you.
And folks out there, first of all, you heard up front, it became a bit of a competition. So put in the comments who won. Did Mark with his metrology
Oh, come
beat
on.
Dan with his nuclear? What does the audience say?
Dan's a good guy. I'll vote for Dan just because he's a good guy.
You're both good guys. I appreciated having you both on. And as always, for those of you out there, I really appreciate you. You are why we're here. And we're here at least every Tuesday, sometimes even Thursdays too. So tune back in. We'll have more informative shows. I can't promise they're all going to be as informative as what Mark brought us today, but they're all going to be at least a little informative. So thanks again. This is Jim Vinosky from Manufacturing Talk signing off. So long.
Thanks for tuning in to Manufacturing Talks with Jim Vinosky. Watch for new episodes dropping every Tuesday. And don't forget to like, share, comment, and subscribe.